Hi folks, we're going to take a look at number 19 from page 364. So let's take a look at the question. It says that three forces are acting from the corner of a rectangular solid along its three edges. And they want us to, first of all, calculate the magnitude of the equilibrant of these three forces. So we know that the equilibrant is just the vector that's equal and opposite, or equal in magnitude and opposite in direction of the resultant. So if I find the magnitude of the resultant, I'll have the magnitude of the equilibrant. Okay, so that's what I'm going to focus on. So what's a little tough about this problem is that we have to try to represent a 3D scenario on a two-dimensional piece of paper. Okay, but I'll do my best here. So I'll start by drawing a rectangular prism. Okay. So here's my rectangular prism. Okay. And we have to pick one of these corners. It doesn't specify which corner it's going to be, so I'll pick this corner here. And it says that it extends from the corner along the three edges. Okay, so I've got a 5 Newton force, I've got an 8 Newton force, and I've got a 10 Newton force that are acting along the edges. Okay, so if they want the equilibrant, the first thing is to add the three vectors to find the actual resultant, to find the net force. All right, and since the order doesn't matter, I can draw these in any order. So I'm going to start with the 2 at the bottom here. So let's say this is the 5 and the 10. Okay, the way I've drawn it. All right, so here you have to imagine that this is a 90-degree angle. Okay, and I'm just going to add them tip to tail. So I'm going to bring this here. Okay, and so this vector is going to look, let's get another different color here, is going to look something like this. Okay, and you realize that we've drawn a right angle triangle, okay, because these two vectors are 90 degrees, so even when I flip it over, it's still going to be 90 degrees. Now, just to be sure, let's draw this on a separate little diagram. Okay, so if this is my 10 Newton vector and this is my 5 Newton vector, okay, this is going to be my resultant. All right, so in the end, I have a 90-degree angle. This is 10. And so if I want to find the magnitude, and that's all I'm interested in right now, if I want to find the magnitude of this vector, I just have to use Pythagoras. Okay, so if I call this vector A and I call this vector B, all right, let's just calculate the magnitude of A plus B. All right, it's just going to be the square root of 5 squared plus 10 squared. Okay, so 125, so square root of 125. Okay, so now what I have to do is I'm going to add A plus B to what I'll call C. So say this is vector C with magnitude of 8. And this is where I realize, again, these two vectors, because this is on the bottom face of the rectangular prism and this is going straight up, I'm going to have another right angle triangle. So somewhere in here, this is going to be a little tougher to draw because now I'm really in 3D. Okay, I guess it'll be something like that. Very tough to draw here. I'm going to have an angle that's inside the box. So just to make it a little clearer, I'm going to draw a picture here. So I've got my 8 Newton vector here, and now I've got on the bottom my root 125 unit vector, or Newton vector. All right, and so when I add these two together, there's my resultant. Okay, so if I call this A plus B and now plus C, I can calculate the magnitude. So magnitude of A plus B plus C is again going to be from a right angle triangle, since these two vectors have to be at right angles to each other. So I've got the square root of the square of 125. Oops, 125, and then I've got plus 8 squared. So what do we have here? We have 125 plus 64, and that is 9, 8, square root of 189. All right. So since this is the magnitude of the resultant vector, okay, so if we call the resultant vector A plus B plus C, okay, we have that the magnitude of the equilibrant vector is going to be the same as the magnitude of the resultant vector, so just the square root of 189. All right. Now, when you think about it, you've seen something like this before when we were determining the, so I'll call this A here, when we were determining the vector that joined the two opposite corners of a rectangular prism or of a cube, you just ended up using Pythagoras twice. Okay, and that's exactly what we did here. So that's part A. Now part B, all right, and this is where I'm actually, part B is going to be a little tough to show here. So I'm going to do is I'm going to attempt, I'll see how this works. I'll bring this up here as high as I can, and we'll see if we can represent this in 3D. All right. So what this represents is the bottom. I think I drew this a little differently before, so you'll hopefully get the picture. Is what I have is I have two of the vectors that are on the edges on the base of this rectangular prism, and then here I've got my vector that's coming upwards. All right. And so first I add the first two vectors, and I get this vector that's along the bottom face of the rectangular prism, and then I add these two vectors together, and I get my resultant vector. Okay, now this is where I want to, if I can hold these two together, is I want to try to demonstrate how I'm going to find the angle, okay, from the resultant vector to each of these three vectors, and then from there I'll be able to find the magnitude, the value of the angle to the equilibrant vector, okay? And what I want you to imagine is that if I place line here, I want you to see that I'm going to get a right angle triangle. Or if I place a line joining the resultant vector with this here, I want you to see that where my finger is at the bottom is a right angled vector, not right angle, and same thing here, that if I place this line here, I'm going to get a right angle triangle in that area there. Okay, and where does that come from? It comes from that diagram that I drew before. This idea that when I add two vectors that are perpendicular to each other, the resultant vector is going to be perpendicular to each of the original vectors. So we see right angle triangle there, right angle triangle there. All right. So again, just to try to represent this here, that this resultant vector forms a right angle triangle with each of the original vectors. Okay. But if I take this here and I realize, oh, wait a minute, this is a right angle triangle where the adjacent side to this angle is just the magnitude of the original vector, and the hypotenuse of this triangle is just the magnitude of the resultant vector. Okay, so I want you to keep in mind that that is the adjacent to this angle, and this is the hypotenuse to this triangle here. And so we can use that to find the angles. All right, so I'm not sure if that helped. Hopefully it did. Okay, so let's go back to our problem in here. Let's see if I can, show this here. So again, once I find this resultant vector, I see that this angle is part of a right angle triangle between one of the original vectors and the resultant vector. All right, and if I look at this angle here, this represents the adjacent side, and the resultant vector represents the hypotenuse side. All right, so if I want to find the angle to the 8 Newton vector, I'll go backwards. I'll call this theta 8. Well, that's just going to be cos inverse of, adjacent over hypotenuse is 8 over square root of 189. All right, so let's calculate that here. cos inverse of 8 divided by the square root, the square root of, whoops, wrong one. Let's start again. Cos inverse of 8 divided by the square root of 189, and that gives me 54.41. Okay. But of course, I'm not looking for that angle there. I'm looking for the angle from the equilibrant to that vector. So that's just going to be 180 minus the angle that I found. So we saw that the relationship between the angle of, so if this is the resultant vector, this is going to be the equilibrant vector. So if this is theta 8, this is just going to be 180 minus theta 8. So what I'm looking for here, the angle equilibrant for 8 is going to be 180 minus that. So minus 180, so 125.58. Okay, and then I'm going to do the exact same thing for the other two angles. So for 10, it's just going to be cos inverse of 10 over square root of 189. All right, so let's calculate that. Inverse cos of 10 divided by square root of 189, and that's going to be 43.33. All right, but of course I want to the equilibrant, so I'm just going to take that away from 180, so 136.67. Okay, so equilibrant to the angle, to the vector with 10 Newton magnitude is going to be 136.67. All right, and then lastly, I'll calculate theta, what I'll call theta 5. Okay, and that's going to be cos inverse of 5 over square root of 189. All right, so let's take inverse cosine of 5 divided by the square root of 189, and we have 68.67. And so if I want the equilibrant of that one there, okay, that's just going to be, subtract 180, that's going to be 111.33. All right, and so there we have it. There we have our three vectors. Now, I would like you to try to keep this question in mind, because this idea of finding the sum of three vectors, okay, and then finding the angle of the resultant to each of the original vectors, okay, and then the one up here is going to come in very handy for us very soon. All right, that's it for this one.